Hello, this is Professor Brothers, and this lecture is Reliability Analysis and Design. This original slide deck was from Professor Kenny. So we're going to look at a couple of things inside the slide deck: device failure mechanisms, the mathematics of reliability, designing for longer-term reliability. So first, let's look at a power MOSFET structure. So if you look at this MOSFET, this diagram that's in the bottom of the screen, you can see that there's a vertically diffusing power channel. And so the heat is getting conducted down, and there are multiple layers of different materials that are propagated through here. So there are different contacts between those different layers that are undergoing different temperature gradients over that entirety. And if you look at the diagram that's in the bottom left, you can see more of a thermal scan where there's the hot part and you can see the dissipation down into the mounting surface underneath it. So when you think about this, when you think about how this electronic device operates and how the electrical charge that's flowing through also causes the temperature to flow down into the underlying material that's below it, a lot of mechanisms, the failure mechanisms, are going to come to pass through the heat and through the heat dissipation. So electromigration is one of the first areas that we're going to look at. That's metal ions move under influence of an electric field at high current densities or high operating temperatures. So again, we're looking at high currents, high operating temperatures. Dopant diffusion, the concentration shifts slowly due to solid diffusion at, again, elevated temperatures. Breakdown, oxide or other dielectrics breakdown occurs at high voltages. So far we have at high current densities, high operating temperatures, elevated temperatures, high voltages, then mechanical stress. Specifically, we're going to get die cracks in response to thermal expansion and contraction. So again, a variation in temperature. So if we look at all these things combined, device failure becomes more likely as you operate the device closer to its max voltage, its max current, its max power, and its max temperature ratings. So these four different regions of breakdown can occur individually or in combination. So we're going to look at this and we're going to think about the bathtub curve. So on the left-hand side of the curve, we have what we're going to call infant mortality. Then we have a steady state failure, and then end-of-life wear out. If you think about this in terms of an automobile, a car, there are those cars that are just produced on a Friday afternoon, and they're just weren't built well. They might have workmanship defects, they might have defective materials, etc., and they're just a lemon coming off the lot. They are immediately going to die, and there's nothing you can really do about it. So that's the entry of this bathtub. Then there's the steady state failure. This is where you have a good car, but just as you're driving, something will go wrong, and it has a failure throughout its lifetime. But then most vehicles, you get to about 100,000 miles, and that's when they just start wearing out due to the end of life. And so you can see that there is going to be an increasing number of end-of-life wear-outs the further and further past the expected operating time that you go on that vehicle. Now, this end-of-life wear-out, this region, can be accelerated due to those things that we were talking about on the previous slide, the high temperature, the high voltage, the high power. But for the majority, we're going to focus here on the steady state failure, and we're going to look at some of the statistics about how that comes to be. So in that steady state region, that flat region of the bathtub curve, they can do testing to usually look at what happens at an elevated temperature to accelerate the failure rates. So what this is going to do, it's going to be a total number of units at time is equal to 0, the total of units that have failed at some time t, and then the total number of units that have survived. Now, obviously, there's a relation between these. The surviving units plus the failing units equals the total number. So we're going to define a per unit time failure rate, H of t. So H of t is the number of failures per unit time divided by the total number of surviving units. So this gives a per unit time failure rate. So this can be oftentimes thought of as a derivative. So if we look at the derivative in time, the change in the number of units over the change in time divided by the surviving. But if these are a constant, then these become much simpler to work with. So if we take this and we do the substitution that we were talking about, because the number of surviving and the number of failing combined gives the total number, and then we can factor it out to give a constant term, we can see that the derivative of 1 minus this constant term of ns over n naught divided by ns over n naught is going to be equal to the h of t as well. So note that n of s, n of f, and n naught have integer values. So for a larger number of units, we define a reliability function to be a real valued function that is defined as the number of surviving divided by the total number. That's this constant ratio term that you can see that's being developed as h of t. Then, if we want to think about this in the opposite relation, we can say that the failure rate function, h of t, is given by dt of 1 minus r of t divided by r of t. We can factor this out and come to this relation. All right, so looking at these numbers, one of the things that you want to think about is really what this represents, the change over time of the number of failures given this total constant number. We can approximate this if we have a lot size and we have just a change in time. We can do this division to get the h of t. The h of t can be related to the r of t. More specifically, if we want to create a relation between h of t and r of t, we can distribute this fractional term, the dr dt, we can distribute this dt to the other side, multiply that over to the other side, and so we get negative h of t dt is equal to dr divided by r. If we take the integral of both sides, we're going to get on the right-hand side of this term the integral of 1 over r dr. That gives us the natural log. On the left-hand side, it's negative integral of h of t dt. So if we solve that down, we can see, and we solve for this r of t term, we can see that if we assume that h of t is a constant, which it should be a constant over this duration of time, so that solves out to be this form. So the initial condition requires that a is equal to 1. This makes sense because at the beginning of this test, no devices have failed. And so this ratio is going to be equal to 1. And since the ratio of the number of failed, or the number of survived, to the total number, when you start off, none have failed yet. That is the assumption because we're only operating in this steady state region. So the bottom of the bathtub is linear, and the bathtub curve shows ht usually found to be approximately constant. So we're making this approximation that h of t is approximately constant. This is an approximation, and that's how this solves out. Given all that, here's the main takeaway. The reliability of any one device is exponentially decaying function of time. So if we have this function r of t, the r of t is the number of surviving units. This is the cumulative probability of not failing after a time t while being placed in a steady state operation at t is equal to 0. We can look at this conversely. We can have the number of units that are failing, so the cumulative probability of failure after a time t, after being placed in a steady state of operation of t is equal to 0. So since these two conditions are mutually exclusive, it holds that the rate of surviving plus the rate of failing is going to equal a probability of 1. So you're either going to be a surviving member or failing member, and if you combine those together, you're going to have all the members of the 100% probability. So big R is the cumulative probability of not failing. Then little r we're going to define as the probability of no failures at a time. So dr dt is equal to little r. And the same thing with f of t is df dt, the probability of failure at a given time. So from the above, it then holds that dr dt plus df dt is going to be equal to 0. If we take that a little bit further, we can define another function called the mean time to failure. The mean time to failure is the average time it takes for a device to fail during steady state operation. So we're looking for the middle of that bell curve of failures. The mean time to failure is the integral from 0 to infinity of t f of t dt. From above, note that f of t is going to be equal to negative dr dt is equal to negative lambda e to the minus lambda t. And so if we substitute that in, we can see that we get this time constant of 1 over lambda is equal to tau. And so the mean time between failure, if we continue to do the math out, we get lambda divided by lambda squared. The mean time to failure is equal to 1 divided by lambda. What was lambda? Do you remember? Lambda was what we assumed. H of t is going to be equal to lambda, this constant value that's representing the rate of the failure. So the main figure of merit used to rate the reliability of a product, you can usually find this in the data sheets, the mean time to failure. And this is a number that companies report very widely because this is a major statistic in how a product is going to be rated for a lifetime. Now let's go through an example. Suppose your laptop is specified to have a mean time to failure of 50,000 hours, which is approximately 5.7 years. What is the probability that will have failed after 3 years? So we can take this and we can say that capital F of t is equal to 1 minus capital R of t. We can do this substitution into this equation of R of t for the mean time to failure. And this results in 1 minus e to the minus t divided by mean time to failure, where you remember back from here, the R of t was e to the minus lambda t. The mean time to failure is 1 divided by lambda. And then we had the subtraction terms to get the R of t plus F of t is equal to 1. So you combine those two equations together. That's where we get this first part. And then we can get this exponential decay of the second part. When you plug in those values, we can see that there is a 41% probability that it will have failed after 3 years. Now, is this a realistic expectation? This is assuming that you are doing continuous operation on this machine for that entire duration of time. So that's not a very valid operation. So let's now say that we only use our laptop for 8 hours a day, which is still quite a bit, but probably pretty realistic. So you now take 8 hours a day, which is 1/3 of an average day. And so we can now say we're going to find the failure rate given the time of 5.7 years with a duration of operation of 1/3, 0.33. If we plug that in, we can now multiply the time by this 1/3 duration, and that comes out to be a 16% probability. So it makes intuitive sense if we're saying we're doing 41% probability if we're running it constantly nonstop, but if we reduce it by 1/3, it drops down to about 16. It feels right. It's just a realistic number, and we can then think about how this number is going to be affected if you are using not just this laptop as an individual machine, but now imagine that you're using it as a series of things. Imagine there is a system that is a combination of multiple items. So we're not just using a single system. What happens if it is a system of systems? So consider a system comprised of a series of connected devices, D1, D2, Dn. So each component of a series connected together acts as a single point of failure. So imagine the string of Christmas tree lights from the old movies where if one light went out, the whole string of lights went out. That's what we're talking about right here. So each component in a series connected together acts as a single point of failure. If any one of these D1 to N's break, the whole thing goes down. So the system reliability can no longer be greater than the least reliable. It can be no greater than the least reliable component. So if we look at that now, we have to take and apply this equation. We have to take 1 divided by 1 plus mean time to failure of 1 plus mean time to failure of 2 plus mean time to blah, 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 dot, dot, dot. And so that will get the mean time to failure for the system in its entirety. But if we want to look at the capital R's, then we multiply those together because that's going to be a summation of everything that's going on. And so it's going to make it much worse. So say you are designing an LED light strip. Again, back to the Christmas lights. We're putting them in series. Each LED is rated at a mean time to failure of 10 to the 6 hours. Because they're all in series, one LED failure causes a single point of failure for the light string. What is the probability that the light string will fail within a year? Okay, for a year, we can take e to the minus 1 divided by 114 because it's 114 years. For one LED, just for one of these LEDs, just for a single one of these LEDs, the R of 1 year is going to be a 99.1%. Remember, R is good. R is the probability that the product is surviving, that it's still working. So for a single LED, we have a 99.1% chance that after a year, it's still working. We're good. But now if we take 60 of those, we need to multiply them together as we showed by this equation on the last page. R is going to be the summation of all of these together, or not the summation, excuse me, the product of all R1 to Rn together. And so we can do that by just raising this to the 60th power. And so if we have 60 LEDs in the light strip, it now becomes 59.1% probability that this light string will fail after the first year. This is because each LED failure is independent and it's distributed on a bell curve. So if we're thinking about this bell curve of distribution, somewhere in there, the mean time to failure is in the middle, but there are going to be lights that fail sooner. There are going to be lights that fail later. So the probability of failure is the inverse of this, or not the inverse. It's 1 minus the probability of success, and so that comes out to be 40.9%. So there's 40.9% chance that it's going to fail after 1 year. How do we make it work a little bit better? The answer is redundancy. We can do parallel connections in a system. Systems will not fail unless every redundant component fails. So now think of this. We have this f of s is going to be equal to f1 times f2 dot 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 fn. The r's are going to be equal to 1 minus the f of k, which is 1 minus e to the lambda k of t, where the lambda k is the total of it. And now if we look at the system of r's, we can see that that's going to be 1 minus the product of all of these 1 minus e to the minus lambda kt terms, where k is going to be from 1 to n. There's no simple formula for mean time to failure of a parallel system. So that's best done using a spreadsheet or MATLAB. So consider that we have a radar system, and the radar system is being designed for satellite with a mission life of 20 years. An individual radar has a mean time to failure of 10 to the 5th hours, which is 11.42 years. Calculate the number of redundant radars that must be used to ensure a 99% probability of mission life over 20 years. So if you have just one radar, no redundancy, R of t is equal to 11.42 is going to be equal to e to the minus 20, that's the t, divided by the MTTF, the mean time to failure. So that gives us a 17.3% chance that we are going to make it through that 20-year lifespan. Think about that for a minute. So we've got 20 years that we're trying to accomplish. The mean time to failure is about 11, so a little bit over halfway through. So there's a 17.3% chance that we'll still have a radar operational at the end of there. That gives you an idea of the distribution of the mean. So now let's take it a step farther and see that we have two redundant radars, or we have the radar and the redundant radar. So now R of S is going to be equal to T of 11.42 still, but it's going to be equal to 1 minus e to the minus 20 divided by 11.4 squared. That gives us a 97% chance that one of the radars will live. So just by giving one redundant system, it increases it from a 17.3% chance to a 97% chance, but that's still not quite good enough. So if we have 3 radars, so there's the primary and 2 redundant units, that gives us the third equation, and that gives us a 99.5% chance that our system will survive to the end of the 20-year life cycle. Note that the reliability of circuitry used to swap out the field unit is not being considered in this example. So that's saying that as we're operating, there are other factors that you might have to figure into this. So let's go back to the LED example. How can we make that LED string better? Let's say that we redesign it, and now the new strip has 60 LED circuits in parallel. Each LED circuit is designed with 2 parallel LEDs. So now we've actually doubled the total number of LEDs to 120 LEDs, but they're created in a way where there are 60 circuits. Each circuit has 2 LEDs that are in parallel. When we look at this, now we have a series of parallels. So first thing we have to do is figure out what's the probability for the parallel system. So now we can say, okay, we have this R circuit, which we're going to look at for 1 year, and that is 1 minus e to the minus 1 divided by 114, quantity squared because we're doing it in a parallel. So that gives us an R value of 99.9924% that it's going to make it through 1 year. So now let's take 60 of those in parallel. So we do that by applying the second equation, where we can take this interior, put it right here, and then we raise it to the power of 60. And when we calculate that out, that gives us a 99.5% chance that we're going to be operational at the end. So the probability of failure after 1 year is 1 minus R of S of 1 year is equal to 0.5%. This is much better than the 40% failure predicted on the original design. So, and then there's a side note. Note that this assumes that the mean time to failure does not change at the doubling of the current. Now, this likely would create a higher temperature environment or a higher current flow environment, which would change the lifetime of that single part. We're not going to go that deep into the statistics. So if we now start to think about that temperature dependence of mean time to failure, how does it affect it? So empirically derived models may be determined from the accelerated life test by operating many devices at elevated temperatures. And we can also use a model that holds through for these devices, and I'm going to slaughter the name of this, Awareness. Yeah, I'm sorry, I tried. So this model failure of the reference is the reference rate in hours. And then the T reference is the reference temperature in Kelvin. And E of A is the activation energy. we have the Boltzmann's constant, and the absolute temperature. If you see the extrapolated model and then the high temperature test data, they drop almost perfectly on the line. And so we can see that this is a very good model to use. If we have some reference points to drop down, we can continue to extend it using the extrapolation model. So in using this, we could go back and redo the light bulb example and say we're going to double the temperature, what happens? We're not going to go that in depth. So here's a summary of the reliability. Much depends on temperature. The mean time to failure is the figure of merit used in electronics industry and others. Series, systems, circuits, or systems that include a single point of failure greatly reduce reliability. And then a redundant system may be designed to improve the reliability. The main takeaway from this whole presentation: pay attention to the mean time to failure specs and operating temperatures of the electronic devices. And I'm going to expand on that last point, not only the operating temperatures, but also the operating power, the operating current, and the operating voltage. Don't exceed their max. Don't even push their max. So back it off a little bit. It'll really make your devices last longer. Reliability and thermal performance are intimately related. Failure rates increase exponentially with increasing junction temperature, and equivalent DC circuits are used to estimate junction temperature at a given power distribution. Heat may be removed by conduction, convection, and forced air. These are actually relating back to the previous PowerPoint slide where we were talking about thermal. There are some backup slides at the end of this. I'm going to go through these really quick. So one of the things I talked about was the bell curve distribution, about how that can be related. So the bell curve distribution is the probability distribution function. This is where you'd look for the mean, and the probability of each end is going to be decreasing down to 0. But the cumulative curves, these were the capital F of t, and the reliability function, capital R of t, are cumulative. And so these are where we get the derivatives from, and you can see the derivative nature when you compare these two graphically, where you are going to start off at a 0 slope and then reach max and then back to a 0. So here's a saddle point, and then when we come back, we again zero out, and we zero out at the top. The inverse is true because this is a 1 minus. PDF and reliability, the probability of failure, probability of success. Assume the area of the left side is 0.45 and time is 10,000. There are two ways to look at this area. The probability of failure of one device is 0.45. If we think that the test starts with 100 devices, after 10,000 hours, 45 will fail. So you can think about this in a singular view or as a multiple of the number of devices. System reliability, here's where we have two systems in series, and the R of the system is going to be the multiplication of the two. We have two in parallel, and these are going to be the R of the system is 1 minus 1 minus R1 times 1 minus R2. We can combine circuits such as this. This is what we were doing in the LED example, for instance. And if you have a combined system, you can combine these two equations to make much more complex equations for the reliability of the system. Here's our final slide. Let's say that we run a test, we get a failure rate. The failure rate is 0.0001 failures per hour. I might have thrown too many zeros in that. You can convert a failure rate, which is the h of t, into the mean time to failure by 1 divided by lambda. You can also go to the reliability, which is e to the minus lambda of t. Or you can convert between mean time to failure and reliability using reliability is equal to e to the minus t divided by mean time to failure. So these make a triangle. They're all interrelated. Then to get the capital F function from that, we use the R plus F is equal to 1 equation. That's it. I will see you next time.